Okay, can you see my screen?
Yes, so next speaker is Massimiliano Riva, and his title is Gravitational Bremsstrahlung in the Post-Minkowskian Effective Field Theory. Please.
Yes, thank you. Thank you. I would like to thank the organizer for this beautiful workshop and the last week seminars and lecture, and also for giving me the opportunity of talking about this work that I have done with Stavros Moujakakos and my supervisor, Filippo Vernizzi. And what I will describe today is basically the word-line effective theory approach to the binary spiral, to the scattering problem, In particular, I will try to describe this word-line effective theory applied in the radiative sector of the problem. So I will start with a very, very brief introduction of what is the object that we are studying and why we are studying this. And then I will enter in details in describing the EFT, what we can compute in particular. So what we called the classical amplitude, which is actually the waveform in Fourier space, and then the radiated observable, so the emitted momentum and the emitted angular momentum. So we all know that the main goal is to have a clear knowledge and as much analytic as possible of the two-body problem. And we know that the traditional way of studying what we can study analytically, the spiral space that we can study in a perturbative way, and that it is usually studied in post-Newtonian regime, so in the non-relativistic regime, with remarkable precision. But in recent year, the perturbative study in G, so in the Newton constant G, has gained new attention. This sort of study has started during the 80s and the 70s by Pioneer, studying by Thorne, Kovacs, Westphal, and others. And recently, there has been at least 3 main approaches to the study of the scattering problem in this so-called post-Minkowskian perturbative study. The scattering amplitude approach that has in few years has managed to find remarkable results thanks to the using all the technique and developed features of the scattering amplitude, quantum scattering amplitude community. The agonal approach and the word-line EFT approach are other 2 alternative approaches for studying this scattering problem. I will focus on the word-line EFT, and in particular on the extending the word-line EFT established by Porto, Kalin, and Mogul Plefkensteinov to the radiative sector. So how this PM EFT works. Okay, what we start from is the usual Einstein interaction, so traditional GR gravity, coupled to some point particle, because we are in an EFT spirit. We describe the 2 objects that are scattering as a point particle at leading order plus some higher order operator that will eventually encode either spin or finite size effect that for the moment we neglect. And we expand we do a perturbative expansion around the Minkowski metric, and from the Einstein-Hilbert action, the Einstein-Hilbert section of the action, we derive the usual Feynman rule. So we work in the linear de Donder gauge, and we derive the usual propagator for the graviton and self-interaction vertices. And I just want to stress that we keep implicit and flexible the I epsilon prescription, in a sense that there is in this EFT there is an implicit splitting between conservative and radiation modes of the field, and we know that whenever the graviton that we are considering is a potential graviton, so it will never goes on shell, it can be useful to not consider retarded boundary condition because computation can be easier. But one must be treating this I epsilon prescription in with care, because of course, for external on-shell graviton, one need to impose retarded boundary condition, and so use retarded propagator, because we want to take into account only outgoing graviton. So at the beginning, the two particles are free and not interacting. From the point particle section, instead, I didn't mention, but the objects are considered as external sources of the gravitational field, so they won't have a propagator. What we get is are the vertices that sources the gravitational field, and we use the Polyakov action parameterization rather than the traditional square root parameterization. That is because, as you can see in the Polyakov formalism, in the Polyakov form of the action, sorry, the interaction between the gravitational field and the point particle is linear, and therefore there can be only one way to source the field. And this is just the linear vertices that I wrote here. The last thing that we need to do is to isolate the power of G, because as we said, we want to do a perturbative study in the Newton constant G, and in this vertex, the word line X and the full for velocity U will depend, of course, on the gravitational interaction as well. Therefore, what we can do, and what has been done in this paper by Koenig and Porter, you can expand the word line and for velocity around straight motion. So the straight motion variable are basically the velocity of the incoming particle at minus infinity, and then there are a set of deviation from straight motion that parameterize at each order in G the deviation from the straight motion. For the computations that we did, so for the leading order and next leading order amplitude waveform that we computed, we just need these two vertices that I wrote here, basically, so you just need the first order deviation from straight motion. Once we have our set of Feynman rule and a way of understanding the power counting of each diagram, we will compute the pseudo-stress energy tensor via a matching procedure. So we will match our diagrams with an effective action describing a pseudo-stress energy tensor sourcing a graviton, basically, and we will consider just the linear source, so one single possible emission of graviton. We will, for the moment, neglect the multi-graviton emission, because in the classical problem can be neglected for the moment. So via the matching procedure, we can compute the pseudo-stress energy tensor that will depend on not only on the word line, but also on the gravitational field itself. From the pseudo-stress energy tensor, we can compute what we call the classical and amplitude, and it's classical because in all of this diagram, we will never consider graviton loop, and so in this way, we were able to drop from the beginning every possible quantum contribution. So we will compute the classical probability of emitting one graviton, which is directly related to the asymptotic waveform in the Fourier space, as you can see here. Epsilon is just the polarization to tensor of the external graviton that we can take in the transverse tracer gauge for simplicity, actually, to take it on shell, actually. So let's go on the computation of this classical amplitude. So the leading order is very easy. In fact, the leading order is just straight motion, basically. So the straight motion sourcing the gravitational field. The stress energy tensor at first order is very easy as the amplitude. Of course, you can see that at leading order, this stress energy tensor is basically proportional to the delta function of the frequency of the graviton. So this is actually a non-radiating piece in a sense, because it's actually a non-radiating piece in a sense. However, we keep track of this piece because, as you will see at the end, they are actually relevant in the computation of, for instance, the emitted angular momentum. I know that there are, actually I learned a lot about current discussion and subtleties about the emitted angular momentum and BMS and memory effect. I won't talk about that here, but I would want us to stress that we need to keep track of if all of this is well defined, we need to keep track of the non-radiating piece in order to compute the corrected emitted angular momentum. Then we can compute the next leading order as well, which is also not so hard. Actually, it's quite straightforward from the diagram to write down the amplitude. And I want to stress one thing, it's that from this diagram, in which we are basically evaluating the particles sourcing the field, and we are evaluating the word line on the first order deviation from straight motion, we are getting this plus I epsilon condition that basically comes from the fact that when we compute the deviation from the straight motion, we are imposing a retarded boundary condition in the sense that we want the deviation to be 0 at minus infinity, because as we said, at minus infinity, the particles are moving freely. And if one re-expand this retarded boundary condition, then one realizes that you extract other static pieces also from the next leading order amplitude. Therefore, static contribution in this amplitude or waveform will be present at all order. One can expect that they will be present at all order. The other thing that I still haven't defined in this amplitude are these I and J, and these are two sets of master integrals. So the full next leading order classical amplitude can be described in terms of the two sets of master integrals. The first one can be solved analytically quite easily. Actually, the second one is more involved, and we were able to write it as a one-dimensional integration over Feynman parameter. Now, I don't want to maybe bore you with details of the integration, but this is actually one of the greater one of the greatest wall that we are facing right now, because while for the we consider only the scalar integral because the tensorial integral can be derived from this one, while the integral I0 can be computed rather straightforwardly by collapsing to a two-dimensional integral. As I said, the integral J0 is more involved because you end up with one-dimensional integration over Feynman parameter Y of this K1, which is the modified Bessel function of the second kind, and this S is this function that you can see here. So it's not easy. This is actually the greatest wall that we are facing in order to advance for future computation. So one goal is also to find another way and maybe more efficient way to solve this kind of integral that come exclusively from the fact that gravity has self-interaction, basically. But then again, we can anyway do something with this with the expression that we had before. So first of all, we wrote explicitly the amplitude, which is again, which I remember is the waveform in the Fourier domain, by putting ourselves in the rest frame of one of the two particles. That is because it's that is because it's it looks easier and more compact in this frame. We're actually working also to write an expression in the center of mass as well, which is not too hard actually. And you can see this is a rather compact form and not too complicated. And I want to, we have also here explicitly written explicitly wrote the plus I epsilon prescription that I was telling you about before, and we split it in a finite piece plus a delta function, so a non-radiated piece. Here Z is just a rescale frequency, so it's a dimensionless parameter. And once we had this result, what we tried to do was to see if it was consistent, first of all, with known result in literature. And in fact, the only known result that we could find is this pioneer work by Thorne and Kovacs, in which they computed this classical waveform also using traditional GR and equation of motion. However, they couldn't be able to find a full expression for the Fourier domain of the waveform. So what we could do was to check they had an exact computation for the forward limit of this waveform, and indeed the forward limit, our amplitude do matches with the one that they computed. The same goes for the small velocity limit. And the reason why we can solve exactly these two limit easy in an easy way is because in the forward limit basically means that the direction of the emitted graviton is parallel to the direction of the particle that is moving. In this limit, this exponential drop, because the direction n of the graviton is basically perpendicular to the direction of the impact parameter, and then the integration over y can be done exactly. The same goes for the small velocity limit, because z, which I remember it's the dimensionless b omega over v, in the small frequency limit, in the small velocity limit, sorry, is a scaleless parameter. And therefore, when one can expand this exponential in the small frequency limit and solve exactly the integral again. So this is the reason also why they had in their paper an exact expression, analytic expression for these two particular limits. What one can do, it can also compute the waveform in direct space starting from this expression. In fact, if you remember, the master integral I0 and J0 contained a 2 delta function. And when we solved it, we used this 2 delta function to kill basically two components of the Q integral. While when one computes the master integral in the time domain, one can use one of the 2 delta function to solve the integral over the frequency. And what is left is basically a 3-dimensional integration over Q, and you gain a time dependence on the impact parameter. So you get a time dependence impact parameter in a sense. And the 3-dimensional integrals can be written in this way. And we actually checked that starting from our Fourier, Fourier domain amplitude, we reconstruct the exact form that Jacobsen et al. In this recent paper derived, and this expression actually matches the one that Thorne and Kovacs derived in the 80s. So for the moment, these master integral can be solved exactly in direct space, but not in the Fourier domain space. Then once we have seen how to compute the asymptotic waveform, what we can do is to use this waveform to compute radiated observables. In particular, we focused on the emitted momentum, so the momentum carried away by the graviton, and the angular momentum carried away by the graviton, that can be computed in this way. And these are two standard GR formula that can be found in any textbook. What I want to stress is that one expects these two to scale in different way in G at leading order. That is because basically the linear momentum is proportional to 2 time derivative of the waveform. And you can see that whenever you take a time derivative of the waveform, you're basically bringing down a frequency, K0 or omega, of the graviton. And therefore, what you are basically taking is omega times the amplitude that I showed you before. And this omega is basically killing all the static pieces that are inside this amplitude. Therefore, while since the leading order amplitude is purely static, as I showed you before, we can expect that it does not contribute to the linear momentum emission, but it does contribute to the angular momentum emission. Therefore, there will be a difference or a different order of G in the leading order emission of the linear and the angular momentum. So the linear momentum, written in terms of the Fourier classical waveform, can be written in this way, and the measure here is just to ensure that the graviton is on shell, and can be recast in this nice way. And we saw that we confirm again that the linear emission is homogeneous in the power of m, which means that basically this emission is completely fixed by the probe limit, and this is something that already Thorne and Kovacs has shown and in the 78. This function E of gamma has been recently computed using the Keimer formalism and by the scattering amplitude community, and confirmed recently also by the Eichhorn approach. We managed to compute this function E of gamma exactly, while in our case, unfortunately, it wasn't possible, or at least yet it's not possible. We still haven't found a way to compute this exactly due to the involved integration of y that I was discussing before. Now we are working on see how, if there are some symmetry and some subtlety and some other way to write what we have in order to solve this. But what we could do rather easily actually is to compute the expression for this E gamma at virtually every order in the small velocity limit. And that is because, again, as I described you before, the small velocity limit of the amplitude can be computed rather straightforwardly, and because the integration over y simplifies quite a lot. So we actually computed the coefficients of the expansion of this E up to 7 to v to the 7, and this coefficient precisely match the ones that has been computed in this paper by Herman et al. Using scattering amplitude community, using the scattering amplitude techniques. So this is actually maybe the most non-trivial check that we have of our amplitude. And also this coefficient match with some traditional PN computation in the scattering of the scattering problem from Blanchet and Schaffer. One thing that has been also pointed out by Rafael Porto in his talk in the last week is that one thing that the scattering amplitude community maybe has more difficulty to compute is the integrand of this energy, while in our case it's not so hard to find the expression of the integral. It's actually what we can find from the beginning, the integrand of this emitted momentum. So what we saw, the expression for this integrand f, it's rather long. I have it in one slide if you want to see it afterwards in the end. But basically, the main obstacle to compute this E, so basically the most hard part that are in this integrand are these y integration that appears. And we managed to basically reduce to 3 sort of integrals that appears in this expression that are basically proportional to either the sinus or the cosinus of this y zv and dot eb. And then there is also the angular dependence inside here coming from the polarization tensor, but it's actually not hard to take that into account. It's really the hardest part is this wide integration. But one thing that we can compute exactly actually is the, let's say, soft limit, or anyway the small frequency limit of this integrand, so of the energy spectrum. That is because when one take the small frequency limit, one can realize that all the contribution coming from the nonlinearities drop in the small frequency limit, So the small frequency limit is completely determined by this first Feynman diagram that I remember. It's the emission coming from evaluating the leading order graph on the first order deviation to the straight motion. And in fact, the amplitude in the soft limit simplifies a lot, and it's just this this expression where C0 and C2 are just function of the external particle, so either the velocity or the angle between the impact parameter and the graviton. And in fact, using this amplitude, we can compute the spectrum in the small frequency limit and find this result that was computed in the pioneer study by Smar and recomputing more precisely by the Conal group, and we actually match this result as well. The last thing that we can compute, it's the, as I told you, it's the radiated angular momentum. Starting from this formula, what one can realize, that what has been realized by Thibaud in his paper of last year, is that since as I told you, the leading order waveform does not depend on time because it's basically static, one can bring out from the integration over the retarded time mu all the terms that do not depend on time, and one is left with just the total integration over time of the time derivative of the waveform. And this is what is sometimes called the gravitational wave memory. And what can be realized is that when you take, as I told you, the time derivative, you basically bring down a power of the frequency. And this means that you have a power of the frequency coming from the time derivative, and the total time derivative integration basically reconstruct a delta function. And this combination omega of delta omega is basically it's basically telling you that what you need to take of this amplitude is really only the small omega limit. So in a sense, the gravitational wave memory will be determined by the small frequency limit of the Fourier transform waveform. And as I showed you before, the small frequency limit, it's insensible, does not depend on the gravitational strength interaction, and therefore the leading order radiated angular momentum will not depend on the gravitational strength interactions. And that it was something that also with a more classical GR approach realized in this paper. And so more explicitly, one can write the expression for the emitted angular momentum in the in the Fourier domain, and what one is left is just an angular integration, and we recast the form of the integration in this way because it looks like an operator, which is actually the angular momentum operator acting on the leading order amplitude. Here we stripped all the delta function integration, because delta function of omega integration, because we have already integrated over omega. By plugging in our expression of the small frequency limit and the leading order amplitude, we were able to reconstruct the emitted angular momentum computed by Damour, and we found perfect agreement with its result. So yes, to conclude, I hope I convinced you that wordline EFT methods can be very efficient and useful also in computing radiation and radiated quantity in the scattering problem. The main disadvantages that the wordline EFT has normally is the number of Feynman diagrams that it is usually very very big, but as Porto and Kalin showed, and in general as you saw in this talk, using Polyakov action and some smart redefinition maybe of the gauge fixing, you can reduce a lot the number of diagrams that you can compute at each order. And we were able to compute, at least trying to compute, starting to compute the emitted energy and the emitted angular momentum and the waveform in an alternative way, with respect to other method. Of course, what we're focusing, what we really want to do now is to find a way of writing this master integral J in a better way in order to find an analytic expression that can be, yes, that should be equivalent to the one that has already been computed. And this method can be easily generalized by including speed and finite size effect. In fact, I think that tomorrow there will be a talk of wordline EFT with spin as well. And of course, the goal that one need to achieve is also to build a map to connect this unbound quantity to the bound one. For instance, is there a way to connect bound waveform with unbound one, and vice versa? We know that for the observable, at least that for the large intensity limit, we can, it has been built by Raphael Porte and others, a map. Of course, one need to construct maybe a more complete map in the relativist sector. And I guess that's it. I was maybe a bit fast. I hope it was enough clear, but if you have questions, please, I'm very happy to have it. Thank you.
Thank you, Massimiliano. Thank you also for keeping on time, even better than that. Let's see if there are questions.
I have a question.
Who is talking?
Mao.
Mao, yes. Okay, I don't see the hands, but I see.
Oh, sorry. Okay, I'll raise the hand.
Doesn't matter, doesn't matter. I see that it's you.
So yeah, a very basic question in the formulas for momentum and angular momentum in terms of h mu nu. So yeah, so those formulas, do they depend on the de Donder gauge?
Yes, nice question. I don't think, I'm not sure whether they depend on the de Donder gauge or not. They for sure has been derived using H in the de Donder, actually in the, sorry, in the transverse faces gauge, actually, because this H is it's the on-shell waveform. So it really has just two polarization. I'm not really sure whether they can have any dependence on in this sense, because this H is really the on-shell waveform, asymptotic waveform. So when you substitute this H, this basically the index dependence is in this polarization tensor, and the polarization tensor that is used is just the transverse tracer polarization tensor. So I don't think that there is, as long as you keep your gravitational shell, I don't think there is any issue on the gauge.
Okay, thanks.
See, can't you, I don't know, in this connection, I mean, if you take the first equation and contract it with epsilon, lambda, I mean, you can connect epsilon mu nu lambda h mu nu with a lambda. I don't know. I would imagine that it's only a lambda which finally enters.
Yeah. It's indeed actually only a lambda. I mean, because you just contract this epsilon ij, and then they are normalized. So
perhaps the notation is not very
yeah, maybe
clear, but it should be gauge invariant.
Yeah. It's, indeed, when you look at the expression in the Fourier
you
space,
see here
it's,
you have a lambda actually.
yeah, exactly.
Yeah.
Well, it's easier to look at the expression in the Fourier space because it's more clear. You just have the Lorentz invariance measure, and then you just have a lambda square.
Yeah, in fact, in this connection, I had a question. I mean, since your expression, I think, simplify in the time domain, can't you just compute the total flux in the time domain?
Yes, we haven't tried, but it seems that there are quite non-trivial integration even in the time domain. Yeah. We are currently investigating way of doing integration in the Fourier domain, and there are way of writing things looking, for instance, we managed to write the master integral J0 that I told you about as a series, but it's a very non-trivial series, and then it's not clear whether it will resound or whether there will be some subtleties. So it's still an ongoing work.
I know, we tried to, and it's difficult.
By the way, just Thibaut Damour speaking, a small comment. I think it's a bit exaggerated to call Polyakov action for the word line quadratic thing, which had been known, from the very old days, and which had been used also by Brink, Desert, Divekya, Zumino, others in other contexts. I mean, this was known. Polyakov, the importance was for the string. Okay.
Yes, I agree.
Yes.
It's
also just a small remark. Yes, we could not also compute those integrals. So with Donato, we had actually expanded to the 15 order in V, the energy loss. Okay, but we could not resum when the paper of Hermann, Para-Martinez, etc., and others gave the exact formula. So we could check the results, but we could never compute these integrals, in the time domain.
Maybe we discover some new integral unknown
actually,
the mathematical literature.
But I think that in the long term, because, I mean, like everything we heard is purely classical here. You call it amplitude, but you compute the waveform.
Yeah.
All this word line is purely a classical computation of a classical waveform. Why? Maybe the most useful thing, let's say from the pragmatic point of view of LIGO, is the integral computation technology coming from particle physics has had some impressive success. And I must say that I don't understand fully, which integrals you can do. The fact that in the time domains, that they could be done by amplitude method, but not directly here. One should understand better how the integral really was done finally.
Yes, absolutely. Interesting.
We are doing purely classical calculations, right? Our word line method. And actually this integral is not that hard, as you can see from the answer. What you have to do is use the exponential part, the e to the qb at the end. That's just a Fourier transform. You have to rewrite it in a way. We see this when we calculate in the in the impulse. And then the u direction is the only one that gives you a new master, which is this log. But actually this integral, compared to the one that Gregor is going to talk about on Wednesday, this one is actually semi-trivial to the masters that we have right now. Okay. We will include this one when we do the full 3 p.m. It's not very hard. The tree loop was actually quite hard. And this is going to be interesting to discuss why we seem to have different, well, we'll discuss this on Wednesday, whether we have the same masters or not in the tree loop calculation, which was actually much harder than this. This is actually, now we understand this one's very well. From the complete classical point of view, there is no quantum, nothing. Okay.
So Rafael, you say that you were able to do the integrals.
These ones are actually the same integrals that we have for the 3 p.m., except for the u direction that we didn't do. There is one more master, and this is just this log. So these integrals are almost the same that we already have for the conservative part of the 3 p.m. There's almost no new integrals. Now at the next order, we will have new integrals, and that's what Gregor will talk about on Wednesday.
So you can get the closed form expression for this epsilon of gamma?
Yes, Yes,
You
absolutely.
can. You could.
Yes.
Okay. You will show us, or
No, we're not doing
Gregor
this right
will.
now. We want to do the conservative 4 p.m. So we stop the in 3 p.m., for the full 3 p.m., but we'll get back to that.
Okay. Other questions?
Maybe I have a question if I can.
Yes, sure.
Okay, so at a certain point you were discussing the soft limit of the waveform, and you focused
Yes.
on, you were looking at the very leading term. So I was
Yes.
just curious whether you also looked at the first subleading term. What comes after that?
Yes, not yet, but it's something that we'd like to do afterwards as well. We haven't have a final answer for that. Yes, not yet. Yes. Sorry.
Okay, thank you. And maybe another naive question. At a certain point, you had a list of the waveform in terms of the direction along the impact parameter and V. You had A, V, V, A, V, B.
Yes.
Right.
This one, yes.
I mean, this again, I understand it's a way of parameterizing this tensor, right? But we know that there are only two physical polarizations.
Yes.
Right. So there must be some relation between these objects, or?
I mean, these are just the okay. Maybe it's not completely clear, but with this notation. But as you can see from here, these are just the coefficient of the component of the polarization tensor along either VV, VB, or BB. So there are just two really polarization, and they are parameterized by this lambda. So we'll have the very same coefficient AVV, AVB, and BB in front of, let's say, epsilon plus and epsilon minus. This is just a convenience way of rewriting this tensorial structure, but they have nothing to do with the polarization in this sense. The polarization are encoded in this lambda that can be either plus or minus 2 or plus or cross. It depends on what you're using.
So basically, I don't know, A plus or A cross is a linear combination of these objects, right?
Yes.
Yeah. Okay, thank you.
I see also Carlo has a question.
Yeah, thanks. So I'm not sure if I can formulate this in a way that is well posed in the language, because I'm not very familiar with word line. But so comparing with the previous talk, so coming from amplitudes in quantum field theory, to get the waveform eventually at higher orders in G, one is going to need also some cuts of the fine point amplitude as as we just saw in the previous talk. So I was wondering here in this game, if you will still get a linear, let's say, relation between the waveform and this, whatever the word line gives you, so this object with two indices, which for me is the 5-point amplitude, probably for you is a 1-point amplitude right?
Basically, yeah. Yes, I'm not sure. Okay, I know that this what we call this amplitude, which is a waveform in the Fourier space, it's connected to what is called the radiation kernel in the K-Mock formalism, actually, and in principle it should be the same thing. I think in the original paper they showed that doing a classical computation you can see the equivalent with the radiation kernel. I am not sure. Yes, I'm not sure how to answer your question in this sense, because I'm not an expert either in the amplitude sector of the.
No, okay, let me formulate it. Maybe I come up with a different way of asking the question. So if you need to go to the next order in G, would you still need to calculate the same amplitude from your or also something else?
No, I guess you just need to compute this amplitude.
Just the same amplitude, the next order.
Of course, you need to include the next diagrams and possible effect that may arise, like hereditary effect and all this stuff. But yes, you will need just this.
Okay, I see.
What you mean, Carlo, by something else?
No, I mean, just, since we were just seeing in the previous talk that in the amplitude, in field theory setup, you will also need some cuts.
Yeah, but the reason is because you're doing Feynman and we're doing retarded. So what happens is that you rewrite the retarded propagators as Feynman plus cuts. The cuts is correcting the fact that we have retarded propagation in the inside.
Oh, I see. Thanks.
That's what happens.
Now I understand. Thanks.
Very good. Other questions? Well, if there are no other questions, I propose to take a break